Hey everyone, in today's lecture, I want to talk about the impact on slow eccentric contractions on muscle size. I've gathered the research I was able to find on this topic, and by the end of this lecture, I added some practical applications. That way, you could apply what we conclude from the research to your training or to your client's training. So let's start this lecture by asking the question we are trying to find the answer to, which is, do slow eccentrics have an effect on muscle hypertrophy? Hypertrophy meaning an increase in the size of the muscle. So for those of you who are not familiar, a typical repetition in resistance training usually includes three types of muscle actions: an isometric contraction or an isometric action, which is when the muscle doesn't change length while contracting; a concentric action, which is when the muscle shortens; and an eccentric action, which is when a muscle lengthens while generating tension. So, does intentionally slowing down the eccentric phase of a typical repetition impact muscle growth? Well, let's take a look at what the research says. So here's a list of the studies I was able to find and their results. So Shibata and colleagues compared 2 versus 4 second eccentric tempo squats, 3 sets to failure at 75% of 1 rep max, 2 times per week for 6 weeks in 24 male soccer players that have not engaged in any resistance training, meaning that these subjects can be classified as untrained, and two of the subjects actually dropped out, leaving the researchers with 22 subjects. So the participants also took 3-minute rest between sets and had a post-workout protein shake with 25 grams of protein. And what the researchers found was that the speed of the descent did not affect thigh growth, cross-sectional area. However, the super slow descent group built significantly less 1 rep max squat strength, which is expected because strength is velocity specific, but also the faster eccentric group had greater training volume, which could have also caused the increases in strength. Secondly, we have Pereira and colleagues, and they compared a program of Scott bicep curls performed with either a 4 or 1 second eccentric duration by trained men. And the results showed a trend toward greater muscle growth and strength development with slower eccentrics. Thirdly, we have a meta-analysis by Schoenfeld and colleagues, and they found no significant differences in hypertrophy across a variety of tempos. However, there was a lot of heterogeneity in the studies, meaning that the studies were radically different from one another in how they were structured, designed, etc., which makes it a bit hard to draw very good conclusions. That being said, one exception, or one exception was if you were to really slow down the concentric, like 10 seconds done in super slow, because the data shows that hypertrophy is actually inferior if you do that. So if you were to do a bicep curl and you intentionally, keyword intentionally, lift the dumbbell with a very slow speed, lasting like 10 seconds to complete the curl, that type of training is inferior to hypertrophy. Fourthly, we have Samson and Groller, and they compared untrained men performing bicep curls for 4 sets of 4 bicep curls at, at 85% of 1 rep max with explosive concentrics, and either an as fast as possible eccentric or a 2 second eccentric contraction. One set was taken to failure to measure progress and apply progressive overload, but despite that, there was no difference in training loads between the groups. Although the faster eccentric group was expected to perform more reps or lift more weight, no significant difference was found in muscle growth, again, cross-sectional area, strength development for 1 rep max and maximal voluntary contraction, or muscle activation during maximal strength test, indicating a similar neuroadaptation or similar neuroadaptations. Lastly, we have Fisher and colleagues, and they performed a study with actual progressive overload and trained individuals on a full body training program. The traditional train group performed exercises with a 2 second eccentric and 4 second eccentric contraction, or sorry, the traditional tempo group performed exercises with a 2-second concentric and a 4-second eccentric contraction, while the eccentric attenuated the eccentric phase to 10 seconds. Um, Now, both groups trained to failure at approximately 75% of 1 rep max, resulting in up to 6 reps per set for the slower eccentric group and up to 12 reps per set for the traditional tempo group. However, with only 2 workouts per week and about 2 sets per muscle group, there were minimal changes in body composition and the strength improvements were similar between the groups. Now, let's dive a little deeper into why there was a difference between the Shibata and Pereira study. So, while these results from the Pereira study showed a trend toward greater muscle growth and strength development with the slower eccentrics, these differences were not statistically significant. With only 6 subjects per group and the use of ultrasound to measure muscle size, the potential for both false negatives type 2 error and false positives type 1 error was relatively high. On top of that, Dr. Pereira himself has actually confirmed that the total work was equalized between the groups, suggesting that the faster tempo group may not have been allowed to train with heavier weights, which actually limits the study's relevance for practical purposes, where heavier weights are often the goal of a faster tempo. Unfortunately, there was no further clarification on whether total work or only repetition volume was equated, because if there was indeed a beneficial effect, it might be because a 1 second eccentric contraction during a Scott curl is too short to stress the muscle, because that's a speed of almost 180 degrees per second. Because if you let the weight free fall, then you effectively have no eccentric muscle contraction. So the data seems to indicate that a controlled eccentric is better for hypertrophy than an uncontrolled eccentric. But why is that the case? Well, if you were to perform a fast eccentric contraction, what that does is that it lowers the amount of what we call active force production or active tension. Tension being the development of force when a muscle contracts. So, active force production in muscles refers to the force generated by muscle fibers when they contract, and this force is mainly generated by the sliding of force generating proteins known as actin and myosin. So, active force depends on the amount of overlap between actin and myosin, which leads to cross bridging, which is the attachment of myosin to actin filaments. And the more cross bridges that form, the more active force we can produce. So these cross bridges that occur, they take time and energy to form. And when you do a really fast eccentric contraction, you're actually lowering the amount of myosin and actin cross bridging, and therefore the amount of active force production. And what happens when you don't have as much active force production in a muscle, you won't really get the increase in size of the fiber, or at least a lot of it. And it's the increases in fiber size that are responsible for overall hypertrophy. Instead, what a fast eccentric does is it actually increases the amount of passive force production or passive tension. Now, whenever we stretch our muscles, when we get beyond a certain length, they generate force. And as we increase the length of the muscle, the force it generates rises rapidly, even when a muscle is not active. And this occurs in part due to the tissue that makes up the muscle, but also the elements in the muscles that stretch elastically, like the giant protein titin. Now, the role of titin, or the role that titin plays in passive tension of the muscle, is for another video, but essentially, these passive elements in muscles have viscoelastic properties, meaning they possess both elastic properties like a spring and viscous properties like a thick fluid that does not flow readily. And because they possess viscoelastic properties, the forces they produce are higher at faster lengthening velocities. In Titan, this viscoelastic behavior probably comes from the unfolding and refolding kinetics of the hemoglobin or Ig domains it has. But why does the viscoelasticity of these passive elements cause them to produce more force at higher velocities? Well, without spending too much time on that, basically, at high velocities, the viscous components are less able to adapt, thus providing more resistance to the deformation, leading to greater force production. And this phenomenon is actually referred to as the rate dependence. And this behavior can actually be described using the Kelvin Vort model, where the force developed is a combination of an elastic and viscous force. That being said, to put it simply, think about a rapid stretch. Think about a rapid stretch almost in a muscle, which leads to an increase in passive force production. And these passive forces have been shown to cause an adaptation in muscle fibers that actually makes the muscle fibers get longer. And that doesn't really do anything to improve muscle size. There are some mathematical models out there showing how an increase in fiber length can possibly result in an increase in muscle thickness, but we're not going to get into that. So, performing fast eccentrics increases passive forces in the muscle, which can result in increases in fiber length, but that isn't really that important for hypertrophy. Additionally, doing a very fast eccentric contraction has been seen to decrease muscle activation as you're resisting gravity pulls less, and the muscles thus have to produce less force. And since our muscles are generally around 40% stronger during eccentric contractions than the concentric ones, it's plausible that an excessively fast eccentric will not result in enough tension for maximal growth. All right, now assuming the eccentric is controlled, why would slowing it further not improve hypertrophy? In other words, why would going from a 2-second eccentric to a 4-second eccentric, why does that not help, but going from a 1 second to a 4 second does help? Well, from the last slide, we understand why going from a 1 second to a 4 second does help, because we would be controlling the negative portion of the lift. But once we're controlling it, then does it really matter? Why does it not matter if I were to slow it down further and further? Well, when you dramatically slow down the eccentric, you're actually subjecting the muscle to more tension, or you're actually not subjecting the muscle to more tension, but rather more time under tension. However, the time under tension comes at the expense of being able to perform fewer repetitions. So it doesn't improve the overall time under tension because you reduce the concentric time under tension, and therefore the total volume is typically neutral. So as long as you're controlling the eccentric, it doesn't seem to really matter a whole lot. But what's happening on a deeper level is that the overall tension in individual muscle fibers in high threshold motor units, which are the muscle fibers that have the most capacity for hypertrophy, remains relatively the same, and thus hypertrophy remains the same. So, how can we take these results from the research and apply them to our training or to our clients' training? Well, to conclude, rapidly dropping a weight during an exercise might hinder muscle growth and strength gains because it minimizes the eccentric muscle contraction. So, maintaining a control over the descent helps keep tension on the muscles and can also reduce the strain on our connective tissues, as quickly dropping into a squat or a pull up can be tough on the tendons. However, excessively slowing down on the eccentric phase doesn't offer any additional benefits, as the muscles aren't still, or the muscles are still under load until near failure. While slow eccentrics can increase muscle activation per rep, they also reduce the total work done, potentially leading to similar levels of tension on the muscle fibers. And this approach also lowers energy expenditure, but that typically is a minor concern. Now, given that very slow eccentric training is impractical and might negatively affect maximal strength development due to velocity specificity, most healthy individuals should instead focus on controlled but not overly slow eccentric movements. Besides, intentionally slowing or intentionally controlling tempo might become challenging whenever you perform exercises with heavy loads or push to muscular failure, particularly during a very fast or extremely slow concentric contraction. Now, on the other hand, Athletes recovering from injuries might find slow eccentrics beneficial as they can achieve comparable training adaptations with less overall work and less strain on their connective tissues. That being said, it's important to be aware of the limitations from the research. For example, if it was done in untrained subjects, if the training periods were too short, if the sample size was too small, etc. Additionally, how many studies were there to reach a conclusion? These are all just things to consider whenever you look at the research. But as long as from what we can conclude from the research that we have been able to find and see, as long as you're controlling the eccentric and not dropping the weight, then the speed of the eccentric probably has very little impact on hypertrophy, and very slow concentric movements should pretty much be avoided as those are clearly inferior for hypertrophy. My recommendation is to simply push the weight explosively and then lower the weight with control. And as long as you're doing that, your growth will be pretty good.